Okay, so as you saw in the last video that I made, I talked about how to break up vectors into components properly and how to add vectors. So now, as you can see with the title of this video, we're going to be talking about resultant forces. So what is a resultant force? So a resultant force is just the addition of two or more forces. So F1 plus F2, that's a resultant force. F2 plus F3, that's a resultant force. But what we're going to be doing in this scenario with like this little pin, we're going to be doing F1 plus F2 plus F3. So we're going to do all the forces that are present. And the reason why we're going to be doing that so much is just because, you know, as you saw in the first video, it's the sum of the force vectors equals mass times acceleration. So so really in the end, the sum of the force vectors is just really the resultant force of all the vectors that are present. So, and like I just said, that's just going to equal mass times the acceleration vector. But yeah, so like if there was a F4 that was involved in here, we would have to do 1, 2, 3, and 4. So we'd have to add all three of those vectors, but since that's not the case, we just do F1 plus F2 plus F3. So yeah. So just try and take note of this as much as possible, I guess. So that's in the end, that's just what a resultant force is. So it's just the force vector that you get at the very end. Yeah. So anyways, so what we got to do to start off with this problem is we've got to break up all the vectors into components. So the best way to do that is just so we got to well, I guess the most straightforward way for you guys to start out is that we have to write all the vectors with their tail at the origin. So so if we start off with F1, F1 is just going to be like this. So this is F1. And then F2 is just going to be like this. So sorry if this isn't to scale, but it really doesn't matter in the end. You know, we're not trying to be artists here. You know, it doesn't have to be exact. You know, we just have to have a pretty good set of it in the end. You know, as long as you point the vector in the negative x direction and it's in the negative x direction, you know, or pointing in the positive y direction and it's a positive y direction, you know, as long as you have it in the right quadrant, it almost doesn't matter, you know. So, but yeah, anyway, so that's F2 for you. And then F3 is just going to be this guy. So that's going to be theta. Then we have F3 right here. Okay, so yeah. So what we're going to be doing is just going to be finding the resultant force of all those vectors. So really that's just F1 plus F2 plus F3 then. So yeah. So anyways, so what we have to do to first add vectors is just break them up into components, you know, get them into component form, sort of just like how this one's set up already. So yeah, so one thing to note before I continue is that F1, F2, and F3, I picked these in particular because they're different from each other, you know. So F1 is completely in the x direction. So so how would you write that in vector form in the end? Really, in the end, that's just going to be 3 and then 0. So so it's completely in the x direction. So it's literally just the magnitude in the x direction. And since it's headed in the positive direction, it's positive. So so now if we go to F2, that's just this in the end, you know, so it's already in component form. Technically this one was already, but you know, it's completely in a certain direction. So this really trips up a lot of people, to be honest. You know, it's not too straightforward, but it kind of is, you know. It's just you just got to know if it's in one direction, you know, that's the magnitude in the end that you're going to put for that direction. So but yeah, anyways, so then we have -5, 5. And the last one is we're going to have an angle and the magnitude, and we're going to have to convert that to basically component form. So, but yeah, before I move on to that, I just want to talk about how to write vectors also. So So as you saw in the last video, I've been writing them like this, you know. I just prefer this method just because it's a little bit more compact. But you can also write this as just like 3i hat plus 0 j hat plus 0 k hat, you know. That's if it is in 3D. Technically, it's in 2D, so you can almost ignore this. But yeah. So really, all this really means is that well, I hat is just means it's the unit vector in the x direction. So and then j hat is the unit vector in the y direction, and k hat's the unit vector in the z direction. If you have a 3D scenario. So as you see, all of them have hats on them. Really, the hat just means that it's a unit vector in that direction. So unit vector in the x direction, you know, would be in this direction, you know, y, and you know, so on. So if we did the same thing for right here, it would just be negative 5 I hat plus 5 j hat, and then I guess if you want to do 3D also is plus 0 k hat, but you know, we're not doing 3D, but yeah. So anyway, so let me just erase that real quick. Ooh. Okay. Yeah. Okay, yeah, just give us a little bit more space. So for this video series, I'm going to be doing it mainly in this way, you know. I'm not going to be messing with I's, J's, and K's. You can totally do that later on, and a lot of, I guess, physics and engineering professors like to teach in that way, but I don't know. I like this method, so I think it's a little bit more compact, but you know, if you feel more comfortable, do it this way, you know. It's really it's tomato, you know. In the end, it's the same exact thing. So if you prefer one method over the other, choose that method, you know. I just like this method just because it's a little bit smaller to write in the end. Now on to F3. Okay, so with F3, the magnitude's 12. So really, this this side, or the hypotenuse, is going to be 12 in the end. So yeah, so we just need to break this guy up into components, like so, you know. And I guess the components of this guy are more or less like this. So it's negative 5, 5 for F2. So, but I'm going to get rid of that so it's not so cluttered in the end. So, but yeah, so anyways, so really it's going to be headed in the negative x direction and the negative y direction. So I'm just going to, for right now, write down negative x, negative y. So typically, I want to write an x or y, you know, but, you know, since it's the first couple of videos, I'll do it that way. So yeah, so if we go back to trig, you know, if you remember this saying, it's so katoa. So there's a lot of different methods to memorizing this, you know, but really this is just sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and then tangent's equal to opposite over adjacent. So yeah. So katoa. So this is super helpful in the end. So yeah. So if we think about cosine, so cosine is just going to be x over the hypotenuse, which is just 12, and that's just going to equal cosine of 30 degrees because that's what theta is in the end. So yeah. So if we rearrange for x, then we just multiply the hypotenuse on the other side, and we get 12 cosine of 30 degrees. So yeah, so in the end, our vector is just going to be negative 12 cosine of 30 degrees. So now what happens when we do the y? So the y, the y direction is it. So the y direction is going to be the opposite. So that's just going to be y over 12 is going to equal sine of 30, you know, because it's the opposite side. So now if we rewrite this, then we get y equals 12 sine of 30 degrees. So yeah, so in the end we get negative y, so it's negative 12 sine of 30 degrees. So yeah, let me just erase this right now. So sometimes, so I guess you can do it this way if you're not too comfortable with everything, but a lot of times, or basically what I'm going to do in future videos is I'm just going to do hypotenuse times by cosine or hypotenuse times by sine. So I'm just going to skip these steps. So if you don't feel comfortable just yet, do these extra steps that are right here. But yeah, for future videos, I'm going to be doing just hypotenuse times by cosine or sine. So another thing I want to point out is that so we're using the smallest angle possible. So I just want to so just always use the smallest angle. So technically, if you remember from the unit circle, or if you basically, if you have your angle going like this, cosine and sine is going to be negative down here. So technically, you wouldn't have to need these negatives at all, but I want you to always use the smallest angle possible. And basically, that way you don't have to fall for this, I wouldn't say it's a trap, but basically, just use the smallest angle possible because sine and cosine are positive in the first quadrant. So if you have the smallest angle possible, then you'll have then just get your negatives from the direction of the vector, and that's pretty easy as you saw right here. It's heading in the negative x direction, put a negative in front. If it's heading in the negative y direction, put a negative in front of the y component. So technically, if we had positives out in front and we used basically an angle of 210, then we would in the end get these negatives out in front. We would get this negative and we also get this negative. But I don't want you to do that. So don't use the smallest angle possible. Don't use the big angles. Use the smallest angle and then get your negative or positive sign from your graph. Which direction is it going in? Is it heading in the negative x direction or is it a positive x direction? Negative y direction or positive y. So always use the smallest angle possible. So that's just, I'd really recommend that. Otherwise you're just going to be confusing yourself a little bit more and almost setting up yourself for failure in the end. So but yeah. And another thing I want to note out is that so technically we could have used this angle. So this angle is just 60 degrees. So as you remember from trig, cosine is like with the x and sine is with the y. And I guess you see that with like Calc 2 and Calc 3 a little bit, but yeah. So if you use this angle right here, technically your opposite switches with your adjacent, So like cosine is going to be with the y direction, and sine is going to be with the x direction. But typically it'll be this, it'll be like cosine is with the x and sine is with the y. But not always. So just always go back to SOHCAHTOA and figure out if it's a cosine or sine. Don't just assume that it's in the x direction or it's the x component. You're going to use cosine. I've seen so many students just get that wrong in the end. They think, cosine is the x one, sine is the y one. Well, yeah, and when you do calc in the end, but when you're doing physics, just use the smallest angle. And if it's basically if it's adjacent, use or adjacent, it's going to be cosine. If it's opposite, it's going to be sine. And you can never go wrong with that in the end. Yeah. So anyways, so if we continue on with this, we're going to do f1 plus f2 plus f3 in the end, and we're going to get fr. So how you add vectors in the end is you just add the components. So all we need to do in the end is just add all the x components and all the y components, So fr in the end is just going to equal, the sum of the forces is just going to equal, so it's going to be, so the x component is going to be 3 minus 5, and then it's going to be minus 12 cosine of 30 degrees. And then for the y component, it's going to be 0 plus 5, so we're just going to start off writing 5, and then it's going to be minus 12 sine of 30 degrees. So now if we rewrite that and simplify it, it's going to be, so 3 minus 5, that's just going to be negative 2 in the end. So cosine of 30, that's really just the square root of 3 over 2. And sine of 30 is a half in the end. So yeah, so it's going to be 3 minus 5 gives you negative 2, and then minus 12 square root of 3 over 2. So really this is going to cancel with this, and this is going to be a 6 in front. So it's going to be minus 6 square roots of 3 then right here. So now with this, 12 is going to somewhat cancel with this, and it's going to be a 6. So we have 5 minus 6 in the end, and that's just going to give us a negative 1. So this kind of makes sense just because 12 is a lot bigger than 5 and 3. So it's going to basically dominate F2 and F3. Basically, F3 is going to dominate F1 and F2 in the end. So in the end, we're going to get it more in the third quadrant, just because that's the quadrant that F3 is in. So basically, if you look at this component of F2, the y component is canceling directly almost with F3's y component, and F1 doesn't have a y component, so that's why it's going to be negative 1. So as you see, it's a very small, but it, like I said before, it's going to be favored in F3's direction just because it's greater than F2 and F1. I'm pretty sure if we just got the magnitude of F2, it wouldn't be too big. So I think that's just 5 squares of 2, but that's nothing compared to 12. Well, I shouldn't say it's nothing, but but yeah. So anyways, so now if we focus on the x direction, F1 is equal to 3 newtons, and so it's not much compared to negative 5 and negative 6 squares of 3, but yeah. So in the end, that's why this is a lot larger in the end. Well, it's a lot larger negative number. So that's pretty much it then. It's just one more thing is that this is in newtons, and then we're basically all done. So we have our resultant force, and we have it in component form.